I'll focus on electric potential energy. If you remember in class, I showed you about this rock, and I mentioned that the higher I lift the rock, the more potential energy he will have. The further away the rock is from the ground, the more potential energy he will have, PE, because we know it's mgh. So if he's high up, he wants to come down. He wants to be here. The reason for this was to show you that it's very similar to the way that electrons and protons interact. For example, if the ground, let's just say I made this ground here negative charge. I have no idea why I drew the ground again, doesn't matter. This is negatively charged. And up here, let's say I had a positively charged. Maybe the clouds are positively charged. And I placed a proton here. The same thing will happen. He wants to go towards the minus. He does not want to be up. He will be repelled by the positive, attracted by the negative. He has a lot of potential energy there. His potential energy is high. This is not gravitational potential energy in this case, it's electrostatic potential energy. And similarly, if I placed him here, yes, he will have some potential energy, but he will have less. You can compare the arrows. This is a smaller arrow. He is closer to the ground. It's like if I take a rock and lift him here, he will have some potential energy, mgh, but this is a bigger height. This will be more energy. Same idea here. He has got a bigger distance to travel. He wants to be over here. More energy. The opposite is true for an electron. I place an electron here. This is an electron. Now he is close to the minus. He does not have a low potential energy because he doesn't want to actually even be here. He wants to go all the way over here. So the electrons are exactly the opposite of the protons. Now the electron is close to the minus, he will have a higher potential energy. If I put an electron here close to the positive, he will have a low potential energy because he is where he wants to be. So the further away you are from where you want to be, the more potential energy you have. So, to put this into writing, even though we know that two opposites attract, we have to do work to move them away from each other, increasing their potential energy because they don't like to be separated. So these two, proton and electron, they want to be together. They will have some sort of energy. If I make them further apart, like this, that means they will have more energy because they don't want to be separated. They want to be together. He wants to get close to him. So that's very important to know if we have opposite charges or even charges in a field line like this. This is an electric field. We know the electric field lines go from positive to negative. This will be more important later. Let's just figure out what's happening with the charges first. So, as again, if we have two opposite charges, they will repel. So, in order for these two guys to have more potential energy, they have to be brought closer together. I will bring them closer and now they have more potential energy. Because we know a proton and a proton, they will repel each other. They will run away from each other. So right now they have a lot of potential energy. They do not like to be together. Okay, so we know work is the same as potential energy. Well, it's actually the opposite, which is why there is a little negative here. It means that I will do work here and I will use up my own energy and I will increase the potential energy of the system. This proton clearly does not want to be here. I have to push him with a force to make him come there. Great. So that means because we have a force and I moved him some sort of distance, we can calculate the work using the usual formula, W equals Fd. You have done this formula many times before in grade 9 and grade 10. Same formula can be applied here, force times distance. We know the force is this here, F, K, Q1, Q2 over R squared. That might be my Q1, this might be my Q2. And the R will be the distance. Because it's a radius, this force will be the same in this whole radius. A bit like an equipotential line around here. So wherever you are in the same radius, whatever my radius is, you will have the same force, same work done required. Okay, so now we know that. We can put the numbers together, put the formula in. I can take my force I can put it into here, then I'll multiply by the distance. So if I do k q1 q2 over r squared multiplied by r, I will cancel this and I will cancel this. So now I have the new formula over r not squared. So my work or my energy is k q1 q2 over r. That will lead us to this rule here. K stays the same, 9 times 10 to the 9, and if you want to know the unit, it's nm squared over c squared. How is that possible, do I hear you ask? We can just rearrange the formula and find out. We take the formula, we'll replace the r, we'll take away the q's, and you will end up with this rule over here. Fr squared over q1 q2 equals k. Unit for f is newtons, the unit for radius is meters, and of course it's meters squared because it's r squared. And then we have q1 times q2, which is coulomb times coulomb, coulomb squared. That's the unit for k. Another way to find work is if we take our work done formula, and if you remember FEC, F equals EQ, we can substitute that. I can put that into here. Instead of my F, I can write EQ, so EQ multiplied by D, or rearranged a little to get qued. W equals qued. This is most likely going to come up if you have something like two parallel plates, plus on one side, minus on one side, and you can do this. And you can find, using this rule, you can find the work done or the energy inside here for whatever. We have a proton or an electron. This electron wants to go to the left. I will move him to the right by a certain amount of distance, and I can use the rule over here. Excellent. Here is an example. Two charges, Q1, Q2, separated by this distance. Find the potential energy. So we'll use the U formula of charge Q2. It's going to be the same thing, whether it's Q1 or Q2, because the formula includes both of them, doesn't it? Q1, Q2 over R, not squared, just the R. Remember we cancelled the squared when we did the force times distance. K is 9 times 10 to the 9. The first charge is 3 micro, minus 6. Second charge is 4 micro, minus 6. Divided by the distance, 2 centimeters. 2 times 10 to the minus 2, or just I'll write 0.02. Easier to write. Multiply it together, you should get 5.4. Easy stuff. So there's three formulas that you may get yourself confused with, so make sure you don't, okay? We have the force formula, this is Coulomb's law. We'll use K, Q1, Q2 over R squared. This is the main one, the basic one, the one that we started with. And then we used the electric field formula using FEC, F over Q. So we have E equals KQ over R squared. We cancelled out one of the Q's because we're dividing by one Q. So where there was two Q's here originally, we take a Q divided by Q, and that will cancel this Q with one of the Q's. Over here, work done, or energy, K, Q1, Q2 over R, because we multiplied by the distance. So the distance multiplied by one of the R's, because this was R squared over here, that will cancel. You don't really need to know how to derive it. You just need to know that these are the three formulas. This is for force, electric field, and energy, which is for charges. Okay, so if you ever see charges, point charges, that's when you use these three rules, depending what the question is asking for. Another example, we have two charges here, so we will have to use the bigger formula. Two protons, I know the charge of a proton, 2 femtometers apart. Find the potential energy of this system. So there's only two of them. And afterwards you find the speed. We can figure that out. Very easy. Starting with this, protons, 1.6 times 10 to the minus 19. Femto is minus 15. So I'll use K, Q1, Q2 over R. 9 times 10 to the 9 multiplied by the proton, multiplied by the other proton, divided by the distance apart, which is 2 femtometers. Solve it and you will get the energy. Put the numbers in your calculator, this is the energy. And then we can use the kinetic energy formula, because as we know, energy is always transferred. So all of the potential energy will become kinetic energy. That's how we know conservation of energy applies. So half mv squared, we've already found the energy, so that's my E, this Ke will be my energy here, 1.152. Rearrange it to get V. So what we'll do is we'll take the half and the m to the other side, and then we'll take the square root, and then that means V is the square root of the energy divided by a half of the mass. We know the mass of a proton, being a proton, is 1.67 times 10 to the minus 27. And that will be given to you hopefully in the exam. You get it in a information sheet, so you'll know. You don't need to memorize the number. Find it, you have your speed. If you have multiple charges, this is more than one charge, we will have to use the same rule that we already know, but we have to do it between each one. So this is Q1 and Q2, Q2 and Q3, and Q1 and Q3. If it's in a triangle and the distances are equal, like an equilateral triangle, you can make a nice easy one. You can take the r out because it's a constant, K over r, and then you just add the charges inside. And you can actually use this to find the value of one of the charges as well. You have to rearrange the formula. And that is easy enough. Here is another example. We have 3 charges in a triangle. You have to find the total charge, the total potential energy, of this system. So you can do it. You do the big formula here, K, Q1, Q2 over R, Q1, Q3 over R, and Q2, Q3 over R. We know K, 9 times 10 to 9, and multiply the 2 charges together. Remember nano is minus 9, put that into your calculator as minus 9. And you do that between that distance, between this distance, and between this distance. If you do not have the third side, knowing that this is a right-angled triangle, and I did not know this distance, I already know these two because it told me these two. If I have to figure this one out, we'll just use Pythagoras theory. We'll just use this squared plus this squared equals this squared, and that's how we get this distance here, if you're required to do so. Plugging all the numbers in, and you have your answer for the energy. Easy stuff. Great video on potential energy. It's a link that you can click in the PowerPoint. It's on Teams. Click it, and it goes through everything that I've went through. Here is one final example that we already did together. If you want to find the work done in each of these cases, what we can do is bring the first particle to P. Well, there was nothing here at all, so bringing one particle in, he's free to move. There is nobody here. So I can place the first particle right here. And this is 1 picocoulomb, PC. And then what happens is we bring the second particle. Well, now that we've brought the second particle to here, there was already a particle here, and they're both positive, they will repel. There will be some work done. He does not want to actually be here because he is being repelled by him. So 2 picocoulombs as well. Now that we've done that, we have to actually solve the formula. K, Q1, Q2 over R. R they've replaced with L because it's the length of the line here of this triangle. So we can solve it. This times this times this times this divided by the distance equals 1.5 times 10 to the minus 14. Why is it 1.2? It was written somewhere. I don't know where it's written. But maybe it was written in the main part of the question. This is on the instructional guide, so you'll see it. It'll be written in the first part. These are just the questions. Very nice. The next one, bring the last particle in. So unfortunately what we have now is he has 2 forces to deal with. This is another positive charge. He does not like either of the other 2 picocoulombs. He has a force with him, or not a force, an energy. Well, a force as well, but energy I'm talking about because of him, and he will have an energy because of him. And then what you need to do is calculate them both. So Q1, Q3 over R, Q2, Q3 over R. Equilateral, sides are all the same. This is when I mentioned you can take the R out just to simplify it a little. So you'll have your 9 times 10 to the 9. They're trying to be fancy here with 8.99. Both are correct. The hours is rounded. And divided by 1.2 meters. And then you just multiply that by, and then you add all the charges up here. Okay, Q1, Q3 plus Q2, Q3. And you get your energy. The total potential energy, well, you have to find U total. They've made a spelling error here. Very nice. U1 plus U2 plus U3. We started off with nothing. Then we had the second energy due to the first 2 charges. And then we have the third energy due to all 3 charges. And then you now know the total energy stored. Thank you.